I'm analyzing an AdaBoostClassifier model, a type of machine learning model that combines many simpler models. I'll be focusing on how well it performs. The model is performing extremely well on the data it was trained on, 99% accuracy, but significantly worse on new, unseen data, 70% accuracy. This difference is a big red flag. It suggests a problem with how well the model generalizes. I believe the model is overfitting. This means it's learned the training data too well, including its noise and quirks, and can't handle new data effectively. Think of it like memorizing the answers to a test instead of understanding the material. You'll ace the specific test, but fail any slightly different version. To fix this overfitting, I propose reducing the number of weak learners used in the AdaBoost model. N_estimators. Too many weak learners can make the model too complex, increasing the chances of overfitting. Reducing them will hopefully simplify the model and improve its ability to generalize to new data. The model doesn't suffer from high bias. High bias would mean the model is too simple and performs poorly on both training and testing data. That's not the case here. Increasing the number of weak learners would likely make overfitting even worse. I've identified options B and D as correct. Option B, high variance, overfitting, is correct because the huge difference between the training accuracy, 99%, and testing accuracy, 70%, screams overfitting. The model learned the training data too well, including its noise, and therefore performs poorly on new, unseen data. Option D, decrease N_estimators, is correct because reducing the number of weak learners in AdaBoost will simplify the model, reducing the chance of overfitting and improving accuracy on the test set. It's like trying to fit a complex curve to a simple line of data. You're overcomplicating it. I wouldn't select this option. High bias would mean that the model is too simple and performs poorly on both the training and testing data, which is not what we observed here. Think of it like trying to fit a simple straight line to a complex curved relationship. I wouldn't choose this option. Increasing the number of weak learners in AdaBoost would likely make the model even more complex, worsening the overfitting problem. We already have a problem with too much complexity. Adding more weak learners is like adding fuel to the fire. I think this is a good choice. By decreasing the number of weak learners, I'm simplifying the model, reducing the overfitting, which should lead to better generalization and improved performance on the test set. It's like paring down a needlessly elaborate design. I'm analyzing a model built using AdaBoostClassifier, a powerful ensemble learning technique. We'll focus on understanding why the model's performance is significantly different between training and testing data. I see a huge gap between the training accuracy, 99%, and the test accuracy, 70%. This is a classic sign of overfitting. The model is memorizing the training data too well, including its noise, so it doesn't generalize well to new, unseen data. High variance means the model is too complex for this task. N_estimators controls the number of weak learners in AdaBoost. The model's currently using 100, which might be too many, leading to overfitting. I believe reducing this number will simplify the model and improve its ability to generalize. It'll prevent the model from being too focused on the quirks of the training dataset. This incredibly high accuracy is a red flag. It's almost too good to be true and suggests the model has perfectly learned the training data, which is not desirable. This lower accuracy confirms my suspicion of overfitting. The model performs poorly on data it hasn't seen before. There's a significant difference between how well the model performs on known data versus how well it generalizes to unknown data. I'm analyzing the performance of an AdaBoostClassifier model. This model uses a boosting technique to combine multiple, weak learners into a stronger classifier. The core question revolves around understanding why there's a significant difference between the model's performance on training data and its performance on unseen testing data. Wow, that's incredibly high. The model is almost perfectly predicting the training data. This high accuracy, however, can be a warning sign. Oops, the accuracy drops significantly when we test the model on new, unseen data. This is a huge red flag. This is likely the main problem. The model memorized the training data so well that it can't generalize to new data. It has high variance, meaning its predictions fluctuate a lot. That's correct, N underscore estimators controls how many weak learners are combined. Reducing this number simplifies the model, preventing it from overfitting. I expect the test accuracy will get better. No way. Increasing N underscore estimators would make the model even more complex, worsening the overfitting and likely decreasing test accuracy. Nope. High bias means the model is too simple. High bias would result in poor accuracy on both training and testing data. That's not what I observe here. I analyze the situation where AdaBoostClassifier, a powerful machine learning model, shows a huge difference between its training accuracy, 99%, and its testing accuracy, 70%. This is a classic sign of overfitting. The model is too closely tied to the training data and doesn't generalize well to new, unseen data. We'll figure out why this is happening and how to fix it. I see that this is a correct diagnosis. The large difference between training and testing accuracy versus means the model has high variance. In simpler terms, it's memorizing the training data instead of learning the underlying patterns. This is also correct. N underscore estimators is a parameter in AdaBoost that sets the number of weak learners. With too many weak learners, like we have now, AdaBoost can become too complex and overfit. By decreasing this number, I make the model less complex, reducing overfitting and improving how well it does with new data. I find this incorrect. High bias would mean the model is too simple and performs poorly on both training and testing data. That's not what we're seeing here. The model's training accuracy is great. I see that this is incorrect. Increasing N underscore estimators would likely make the overfitting even worse, further decreasing the testing accuracy. I see an overfitting situation with AdaBoost. That's when a model performs great on the data it's trained on, but poorly on new data. Think of it like a student who memorizes the textbook perfectly but can't apply the knowledge to new problems. The question describes a machine learning problem using AdaBoost, adaptive boosting, a type of ensemble learning algorithm. We're given high training accuracy and low testing accuracy, suggesting a problem. I think decreasing the number of estimators, weak learners, will help. Too many weak learners can make the AdaBoost model too complex and overfit. By reducing them, the model should generalize better to unseen data. This is correct. High variance means the model is too sensitive to the training data's quirks and noise, resulting in poor performance on new data. This matches the large difference between training and testing accuracy. The model achieves a near-perfect 99% accuracy on the training data. This is a red flag, indicating potential overfitting. The model performs poorly on unseen data, with only 70% accuracy. This is a clear sign of a generalization problem, consistent with overfitting. Here, N underscore estimators is a parameter that controls the number of weak learners in the AdaBoost model. A value of 100 is relatively high, possibly contributing to overfitting. I believe increasing the number of estimators would make the overfitting worse. More estimators mean more complexity, making the model even more susceptible to noise in the training data. The test accuracy would likely decrease further. The huge gap between training and test accuracy is a classic symptom of overfitting. The model has learned the training set too well, including its noise, but can't generalize well to new data. I'd rule this out. High bias leads to poor performance on both training and testing data. In this case, the training accuracy is great, so it's not a bias problem. That's the core issue. It's a common problem in machine learning, where the model is too complex and fits the training data too closely, hindering its ability to generalize to new, unseen data.